So, I will start talking in Greek. Συνεχίζουμε λοιπόν το session του Hardware and Infrastructure Security και συνεχίζω στα αγγλικά. And we welcome Mr. Michalis Manotakos. A few words about him is that he's an associate professor of electrical and computer engineering at New York University in Abu Dhabi in the United Arab Emirates, and a Global Network University associate professor at the New York University Tandon School of Engineering in the USA. He's also the director of the Modern Microprocessors Architecture Lab. And today, his presentation is on the topic of security evaluation, as you can see, of industrial control systems using system emulation and fuzzing. I remind you once again that you can write down your questions. Please write them down in English so that Mr. Manotakos can answer them as you wish. And I think, Mr. Manotakos, we're ready, and the floor is yours.
Thank you, Donny, for the great introduction. Let me say I speak Greek, right? I'm not just speaking English. So if they want to ask in Greek, I can answer that too. But you know, just to be nice to any non-Greek speaking person who's speaking English, right? It would be nice to have question and answer skills, right? So before I start, I wanted to say something about NYU Abu Dhabi, because there's kind of a weird name, right? It says New York and it says Abu Dhabi. So where it actually is at campus. And I have a slide here. I need to focus on the slides, okay? Actually, NYU has several campuses around the world. One of them is in Abu Dhabi, where I primarily reside. But well, there's one in New York, as you would expect, but there are many more, right? There's one in Shanghai, Sydney, Paris, London. So NYU is embracing the global education and study way. So our students actually move from campus to campus, and they have a chance to be spending a semester in different parts of the world. Well, pre-COVID. Now with COVID, they just do Zoom meetings throughout. But we'll go back to normalcy starting the fall semester. Okay, now on to the technical talk. I'll be talking about the security for industrial control systems. So I need to first define what are industrial control systems. Well, they are what the name says. They're systems that control industrial processes. An industrial process, it can be desalination, it can be chemical processing, it can be the power grid, electricity. So it's something of industrial grade. And these systems are, you can think of them as computers, like you may have heard the term Plc, SCADA system. So they are computers, but they're hardened computers. They're computers that can withstand extreme temperatures, extreme voltages, electromagnetic interference. So not really regular computers, but they're hardened computers, and they also have a lot of interfaces to the real world. They have analog, they can be connected to analog inputs, analog outputs, digital as well. So they have a lot of sensors, input coming in, and they produce output that goes to actuators, like a valve or some other kind of an actuation. And they're part of critical infrastructure that I mentioned already. Power grid has a lot of industrial control systems, nuclear plants the same, water treatment, wastewater facilities. They have those systems inside controlling some part of the process. And as you can clearly understand, the robustness, the fact that they have to be operating properly is paramount for safety, right? And if something goes wrong, something can really go wrong when we talk about critical infrastructure. So we have to, in this presentation, we're worried about the security of those systems. If someone hacks into those systems, they may be able to create some financial damage, or maybe damage to equipment, or even loss of human life. So why is cybersecurity a problem? Cybersecurity is a problem nowadays because these systems have evolved. In the past, they were purely electromechanical relays. You had something that was not really digital, not computerized. Nowadays, we don't use this anymore. We have IoT, industrial IoT, or Industry 4.0 devices, that you have much smarter devices. And in this context, smart means the existence of a CPU and memory and an operating system. So now you may have Linux or you may have Windows in those devices. So this is where the smartness comes from, but at the same time, this is introducing security concerns. So these systems are evolving into typical computers, like our laptops or our phones. They have system-on-chip SoCs coming from third parties, network controllers, DMA chips, or other systems that we use to integrate on the board. General-purpose operating systems, we see Linux, we see Windows in those machines, and many of them nowadays, they're connected to the internet. They offer connectivity, advanced connectivity capabilities. One of them will be internet connection, so you can reach them with regular internet traffic. So what does that mean? It means that in any attack, any virus, any malware, any way we can hijack a regular computer, we can transfer it now to industrial control systems. The same way we hijack a Windows machine, we can actually do that for industrial control systems. We can have a buffer overflow, control flow hijacking, privilege escalation, attacks we see in IT, information technology, now they move to OT, operational technology. So that's a problem, right? And that's why this talk exists, because the systems are very critical. They're now becoming regular computers, so they can be attacked. So we need to find ways to protect them. And this is what this talk is focusing on. So there are problems when we think about the security devices of those systems. First of all, when they're first designed, they're mostly designed for robustness and functionality. That we want to ensure that they work properly under extreme conditions. But the extreme condition never meant hackers. They meant increased temperatures, electromagnetic interference, something like the harsh environmental conditions of a factory, for example, but not cybersecurity. That's a more new thing that we see. Second is, and it piles up on the first problem, is they stay for a long time. The life of these devices can be more than 20, 30 years. So nowadays we have devices installed from the 90s that have absolutely no security, and they will stay there for many years to go. And not only that, the fact that they stay for long, if you don't have a patch management approach or an update mechanism, they have really old versions, right? They may have Windows XP from 2005. So we know so many vulnerabilities that can affect Windows, an older version. So since they are not typically updated, you can use older vulnerabilities to attack them. And the other thing is that they're not really strong computers. They may be computers, but they have a processor that could be clocked in 600 megahertz with memory up to 256 megabytes. That's a typical PLC configuration. So that means you cannot just load Norton antivirus, right? That will just kill the system. You need to find lightweight solutions to improve the security posture of these devices. So these are all the problems that we're trying to work with. The other question I need to address, right, is it a real problem? And this is where I would open it to the audience and ask, do you know any attacks on industrial control systems? But now with this format, I cannot ask the audience. But you may have heard of a few already, right? Stuxnet is very famous. There was attack in New York. There are attacks in the Ukraine power grid. There are lots of attacks. And I need to emphasize, these are only the attacks we know of. There's not much transparency with industrial control systems. The companies mostly hide attacks in order to, they don't really publicize they got attacked by something. So we all suspect there are many more attacks than we see. We only saw a few. Stuxnet, there was a famous one, the attack on Ukraine power grid, or Triton in Saudi Arabia. They're famous attacks, but there are definitely many, many more we don't know of. And we don't know the extent of how bad the situation is currently with industrial control security. All right, so I'm motivated the need for security for industrial control systems. What we do currently is we kind of work in a not proactive mode, right? It's kind of a reactive approach. After the attack happens, we try to fix it. But what can we do to improve security before the attack happens? Can we find vulnerabilities ourselves? But finding vulnerabilities is not easy because you cannot experiment with the system, right? The PLC is in operation, and you should not touch it because you may break the process that is controlling. So this is what the talk is about. How can you find security vulnerabilities of those industrial devices without affecting the devices, without having to take them off without having to remove them from operation, but still manage to understand how bad the security is. So what I'll outline in the next few slides are 3 steps, actually. Well, the first one is easy. You connect to the PLC. So the PLCs have connectivity. You may have FTP connection. Many of them have FTP connection, SSH, Telnet, hopefully not. But you find the path to the PLC and you connect to it. And from the PLC, you download its firmware, you take it out, just files actually. So it's a file copy process. And then you use the copied files to emulate the PLC in an external device. So you take the files you need and you create an emulated instance in another device. And now with emulation, you can play with it, right? You can hack it, you can fuzz it, as we'll see in this presentation. You can do dynamic analysis, static analysis, anything you want, because this is not a real PLC, but you took some files out of the real PLC in order to feed your emulation engine, and then you fuzz the emulated instance and you find vulnerabilities in the fuzz, because fuzzing will crash the PLC, right? So now you're just crashing the emulation, and this is it, right? That's what the whole presentation is about. You emulate the PLC and then you fuzz the emulated instance to find vulnerabilities. That's what we'll see in the next slide. And in this way, actually, you now have non-intrusive assessment. You're not really affecting the PLC. The only way you affect it is you just copy files from it. But this is a standard process of the PLC, because when you send your program, you copy your industrial program to the PLC. So file transfer is a standard operation that you can do in a PLC, even when it's in operation. So we'll just copy some files out of it, and we'll use it for emulation and fuzzing process. And what I'll show today is that we'll do that in the context of codesys. That's one of the most, it's one that be used by several manufacturers around the world. So codesys is actually is an evolution of PLCs. So in the past, every vendor would do its own thing, would have its own proprietary operating system, on proprietary hardware. But as you can understand, that doesn't scale very well. You cannot have advanced capabilities, right? If you want to have, for example, encryption, you have to create your own OpenSSL library. If you want to have web server, you need to create your own Apache capability, right? So this doesn't scale. And what vendors are starting to do is them bringing regular operating systems. So codesys is using Linux with a real-time patch to support on a PLC, right? So now we have PLCs running Linux. And this is great. This is not a bad thing, actually, because Linux has all these amazing open source libraries you can just take. OpenSSL is an example, Apache, Kerberos, anything you want to use, it's there and it's robust, because Linux actually is very well maintained. Imagine a vendor with 5 people trying to have a proper cryptographic implementation, a proper web server implementation, and maintain it forever, right? It doesn't scale. It doesn't work. So the evolution is to use open source libraries with a regular operating system like Linux in this case. So now we have, but at the same time, the vendor would have its own proprietary stuff, right? So on one side, you have the open source, for example, the operating system. You can see the cursor, right, Adoni? Okay. So you have the open source, right, like the real-time Linux, but many of the services provided by the PLC are open source libraries. I mentioned a few, SSH, Apache, and others. But mixed with that, on the PLC software, you have also proprietary libraries. You have the PLC runtime, is where the control logic will be executed on. You have PLC code, for example, ladder logic, structured text, that is how you program a language that you program the PLC, and it's compiled for the PLC. It's not a standard language like C++, but it's special language for PLCs that has a custom compiler and still becomes a binary, right? And then you may have other proprietary libraries like Modbus communication. Modbus is an industrial protocol that are also compiled by GCC, but they're proprietary software. So you see this weird mix, right? You have proprietary code, you have open source code, and they have different maturity and security. They have different way of understanding vulnerabilities, and there are different compilers involved. So you may have bugs from GCC, but you may have problems and vulnerabilities coming for these custom compilers that you have from the PLC code. So Codesi's runtime, right? So I mentioned here you have the PLC hardware. Nowadays, it could be an ARM processor with some standard SoCs on it that will run Linux real-time operating system. And on Linux, you have a process that is the runtime of the PLC. Think of it like, for example, the Python interpreter, right? So Python interpreter will run a Python program on it. So here the runtime is running the PLC binary. So the PLC binary is the control logic. If you have a PIT controller, you have some input to the controller and some output, right? So the PLC binary will be controlling that interaction between the sensor coming in, then from the sensors and the output going to the actuators. So the PLC binary is running on the runtime. And the case study we're discussing, Codesi, that has like 25% of the market. If you look at the code, so this is one of the PLCs we're experimenting with as a WAGO PLC. So if you look at the contents of that PLC, you see that the runtime, the control logic runtime, is running in the boot process of the system, of the PLC itself. And you can see it's a daemon within Linux. And when you're looking at within that process here, what you see is that it has actually many threads, right? And the threads from the PLC tag itself, but it could be the Modbus communication, it can be the communication to peripherals, KBus, or other things, scheduler, and so on and so forth. The very interesting thing about those, that PLC stack, the computational stack of the framework, is that the binary of the PLC is loaded in the stack, and the stack itself is executable. So whoever understands security, right, understands that's a bad thing. Executable stack is inviting vulnerabilities because you can send things to the stack, your payload, for example, and then you can redirect the stack pointer to the payload, and you have now remote code execution. So you have a big problem here. And actually, there's nothing else you can do in a way from Codesi's perspective, because they want to have their own interpreter, their own runtime, and the runtime has to load the file and execute it and control it, right? So it has to load it in the stack, and it has to make the stack executable in order to execute that binary directly. So, well, they could fix it, but they're not, and this is how their ecosystem works. So what you need to keep from this slide is that the PLC control logic is running on an executable stack. That means you can actually try to find attacks to that. So the runtime itself, in terms of security, I personally am a big fan of it. I think it is the evolution of PLC implementations, but still it's evolving, right? It has changed versions from 2 to 3, and with so many security changes in the 3rd version. But you see here on the slide how the CVEs are increasing over the years, right? We see more CVE is a vulnerability that you report to the vendor. So we see more and more of these vulnerabilities showing up, and in increasing numbers. And many of them are extremely critical. And most of them are about problems that we see in regular software, like uncontrolled memory allocation, privilege escalation, exploitable code execution, or remote code execution through a heap overflow. So these are regular IT attacks. Whoever is familiar with application security, this is what we see in regular applications. But now we see these attacks on a control system that's controlling critical infrastructure, like the power grid or a nuclear plant. So this is why it's serious, right? And we need to understand the security posture of this device and try to fix them. So the PLC control application, again, I said it many times, right? So think of the control logic as, again, PID controller. You have an input to it, an output, and you have proportional integral derivative functions that, you feed it an input, you have an output coming from it, and you can control something with it, right? So these mathematical operations will be compiled and become a program, and the program will become a standard binary, a regular binary. So this is what I call the PLC binder. So you have your regular language, PLC language like ladder logic. We'll see the few languages in the next slide. And you compile it and it becomes a library. And then this binary is being loaded in the runtime, and the runtime executes it on the PLC. Again, the PLC is a computer that runs Linux. So the runtime is a Linux process that will load that PLC binary in its own stack memory. The languages, the PLC languages, are standardized by C. There's ladder logic. You may have seen it. You may have taken a class in process engineering. So ladder logic is the simplest, it has coils and other things, and it disables a ladder diagram. That's why the name. And it has inputs, outputs, and the functions that connect the inputs to the outputs. Right. So here you just add one to the input. So that's a very simple PLC program. It receives an input from a sensor, it adds one to it, and sends it to the actuator, to the output. Then you have functional block diagram. That's another standard language. It looks like ladder logic, but it's beefier, as we say. It has a bit more capabilities. And then you have structured text. That's something like a more regular programming language. It's actually based on Pascal. So that means it's much more complex. So you write code in a similar fashion that we write code for standard C or C++. So you have your if statements, you have your switch statements, you have your function calls. So now you understand we're going closer to implementations that we can exploit, because if you have, for example, arrays and you don't do a bounds check, then you can do a buffer overflow attack and manage to have remote code execution. So so the binary itself, that here this control logic, when you compile it, it becomes a binary, right? And this binary will run in the context of the runtime. So this Codecil main process will load the binary that was created from those languages, and will create a new thread for it. It will parse the binary. It will push the binary code to the stack of the new thread, and then two threads will be created, one for the cycle, the scan cycle, because a PLC, right, the control system, is doing the same thing every 1 second or 10 seconds or 1 nanosecond. And the other one is actually responsible for communicating with the peripherals. So it creates those two threads, and then the main thread dies, and now you have two threads running the PLC binary. But again, these threads have the binary in the stack. And then they execute. So as I said, the PLC task is handling the logic, and the other one is handling the scan cycle. So one is reading sensor, for example, and it sleeps. The other one will actuate, right? If a sensor gives you an input, then you do something to the valve, for example. All right. So the threats to that is, in compilation, when you compile that binary, sometimes the compiler can find security problems, right? If you try to exceed the bounds of the buffer in compilation time, then the compiler can see it and warn you, saying, hey, you have a problem there. But there's some things that the binary cannot, the compiler cannot see when you compile the binary. For example, if your input is a variable and is being used to index an array, then you don't know whether this will be out of bounds of the array. So here the array is of 10 elements. This input one could be number 12. Now you have an out of bounds read, right? And you can have an out of bounds write as well. So the compiler cannot predict whether you do an out of bounds read, because that's a variable coming in. 5 minutes, that was fast. Okay, and I'll quickly go through the rest. So what we're trying to do here is to the first challenge we have is that the compiler has problems and weaknesses. It has a lot of third-party libraries, which they're coming from different places, and so it creates vulnerable binaries. And the second is that we cannot play directly with the PLC, because if we break them, they're expensive, they're slow, and then you have to engage them, right? So to address challenge one, we do fuzzing. So we play with inputs to the compiler, and we will try to find vulnerabilities. And challenge two, we do emulation. Fuzzing is when you send unexpected inputs to the program. So the program is asking, what is your name? And you reply with -1, right? I mean, it's not expecting that input. That's not the name. But this weird case may create a vulnerability, may be a vulnerability, because it doesn't expect it, it crashes, and maybe you can exploit that. So fuzzing is sending weird stuff to the program. And you can do it in many ways. You can look up fuzzing. It's a big topic by itself. Emulation is the other thing we do. Emulation takes your standard, your hardware, and creates an emulated instance for it. So instead of working with a PLC, you create an emulated instance, like Kimu is an emulator, right? And then you don't work with a PLC anymore, you work with emulated instance, and you can have many of them. So you don't need to buy 100 PLCs to do 100 parallel fuzzing sessions, but you can have 100 emulated instances and you fuzz each one of them. So this is exactly what we do. So we emulate the PLC, we take the firmware out of it, we extract it, we extract the kernel configuration and the file system, and then we create the QEMU disk image that we use to boot an emulated instance. And then we take that and we fuzz it. And this is where we find vulnerability. So now, see, we don't really attack the PLC. We just take the files out of it, we create an emulated instance, and we fuzz it, and we find vulnerability this way. I'll be very happy on a separate occasion to talk about the technical details. You can find them on the paper. Since I don't have much time left, the many challenges associated with that, right? How do you fuzz? Because you cannot just give inputs to the binary. The binary is a control logic binary, and it scans a cycle. So you have to play with the memory, with the timing to the memory. The many problems when you try to instantiate fuzzing for industrial control systems. And it's a big problem we try to address. You can see here the setup, that's the PLC, and that's the fuzzing session that we implement on the emulated instance that runs on our computer. Result-wise, we actually see the crashes that we would see on the PLC. We see the crashes also at the emulation instance. So we don't miss things when we do fuzzing on the emulated instance. And it's not invasive because we take just the files out and we do the fuzzing on the emulated. Here, you have information about the crashes. We'll have a few crashes, but then you have to manually analyze each one of them to see whether you find some vulnerability. And you can see how many crashes we get per hour in different functions, right? So every function would create a crash one way or another. And maybe not all of them can be exploited for remote code execution, but definitely just having a crash is enough for a DOS attack, right? Denial of service attack, because you crash the PLC. You may not take over it, you don't do your own code execution, but you crash it, right? And that's bad enough. It's a denial of service attack. More information about the execution speed. The good thing about fuzzing and emulation is that you can do it much faster. So you can do emulation. If you fuzz the emulated instance, it's way faster than fuzzing the PLC because the PLC is slow. It's a slower processor with less memory. So actually emulation gives us the benefit of speed as well. All right, I'll stop here. I think I'm out of time. The technical content, we actually have a paper that will appear on Usenix this summer in August. And the paper is already available on the Usenix website. That's for the fuzzing part. And for the emulation part, we have a date paper that we have. It's also available, I can send it to you, that shows the emulation part of this. And this presentation, we're actually will deliver it to Black Hat in a few days. With that, I'd like to stop and take questions. Always last comment, we're always looking for great PhD students. So if any of you are thinking about the PhD in the future, please reach out to me. I'm very happy to talk to you about a PhD at NYU. And with that, I'll stop and take questions.
Well, thank you very much, Mr. Manotakos. It was very interesting. I wish we could have more time so you could analyze it more. But still, we got a great insight into this section. We have some questions. So, first one, it's more general. Since you have such experience from other parts of the world, what's the situation of H&I security and PLC in Greece comparing to UAE and USA?
So, well, the good thing about Greece is that it's not very advanced. We have a lot of outdated infrastructure. And I personally haven't worked in Greece for industrial control systems, but I've talked to people and they told me that they, for example, has really old relays that are not really smart Greek, right? They're just electromechanical. So now that's a good thing because you cannot hack them. There's no connection to them. They don't have a way you can take them over, right? But of course, things are changing in Greece too. Automation is coming in as well. Actually, US is equally old. US is, you think of it as a technology capital, but still its infrastructure is crumbling. It's very old infrastructure. You go to the subway and you think you're going to die there. US is the same situation as Greece, but now automation is coming in faster there. UAE, actually, on the other hand, since it's a much newly developed country, it has a lot of these devices, automation, and because also of geopolitical issues, it is a prime target, and we've seen many attacks actually in the Middle East. The vendors, though, because they're newer devices, they have better security posture. They already have industrial firewalls. They have authentication mechanisms for PLCs. So it is, at the end, really, it's up to the implementation and configuration of the company itself. Is the company doing a good job, right? It doesn't matter if you have legacy devices or newer devices. It's really up to how the company is creating its security architecture, is implementing security controls, is doing proper risk assessment, risk management. It so becomes kind of an individual instance thing. In the US, there are national directives that everyone has to adhere to. You have to have minimum security critical infrastructure. In Greece, I'm not familiar with what's happening. UAE is centrally controlled, so the government is controlling also the critical infrastructure, and they are pushing for security heavily, actually.
Thank you very much. And another question is, what technical knowledge an engineer should have so that he can operate a PLC?
That's so he can what, the PLC?
He can operate.
Okay.
Yes, go on with this field.
In industrial control systems and critical infrastructure, there are many different expertise involved, right? You have the process engineer that will, there will be an expert in water treatment or desalination or power, and then they'll create a process. And then you have the operation. You have, well, there's a process engineer, there's a control engineer that will create the control logic. And then you have, the operation of the PLC will be done by the operators. That most of them may be just, they're control experts, and they're looking at the HMIs to understand. So to operate a PLC, well, you don't operate it, right? A PLC is automatic. That's the beauty of it. It's an automated, it's a controller that once you set it up, you just monitor it if something goes wrong. So this would be process engineering, control engineering. You have to go to that's closer to electrical engineering actually than computer engineering. And I think there must be classes in your universities specifically on control engineering. If I'm not, Adoni, am I mistaken? There must be classes, right? That you do PLC programming.
Yes, the truth is that we have, but I guess that it's not as well known. It's not too extratameno. Sorry for the Greek.
Okay, yeah, of course.
Yeah.
Okay.
All right, so and another question. What is your advice to young Greek engineers that want to work on H&I security, but are skeptical about going abroad? And this is from a student in his final year. He's an electrical engineer student, and he is interested in this topic.
Well, I mean, going abroad, it's a decision to be made, right? And again, feel free to reach out to me directly through my email or Twitter. Twitter, I don't use much. I mean, I use it as a lurker, but I don't post. I'm trying to change that, though. I'm trying to post more. Going abroad is a life-changing experience, right? I did my undergraduate in Greece, in the University of Piraeus in computer science, and then I did my PhD in the US at Yale. And I'm glad I did, because I learned throughout these years that any change is good. So I changed country, culture, university, and then I learned many new things. and I absorb new things from my new place, right? So I'm carrying all the great things and the bad things Greece has to offer, and you pick up the good things and the bad things the US has to offer, right? And then you kind of, think through all of them. So my advice is always to expose yourself, to gain new experiences. You should, in my opinion, if you have a chance to study abroad, you should do it. Your mind will open up, you'll meet interesting people, you'll change your mind about so many things, and this is how you grow. And you will grow anyway, but abroad and going abroad will accelerate your growth. So, you'll be, I'm now 36. I feel old, right? I don't think I'm that old, but, I think I've seen many things because I let myself be exposed to things. I let myself be in situations that, and I heard that advice, some of the great advice from a friend. He said, if you're the smartest person in the room, you're definitely in the wrong room, right? You always have to be in a situation that you challenge yourself to become better, to grow, to improve. So that's why, when I first went to Yale for my PhD, I felt I was the most stupid person there. In Greece, I was, the top of my class. I had the best grade ever in the university, and I go to the US, and I was the worst there. And there were classes that I have no idea what was happening. They were asking questions, and I couldn't understand the question. And some people were just answering the question perfectly, right? Like, what is this, right? But this is what pushed me to improve. And at the end, I made it, right? And I think all of us can make it if we really like what we're doing and we like the talent. So my advice to younger engineers is to always be in a situation that you learn constantly, you improve, and you always take up on new challenges, because that's how you improve and you become a better person.
Thank you very much, personally, as a young engineer. I have another question. Maybe this would be the last because of time. What has been the most interesting part of your journey up to now regarding your studies, from the moment that you graduated from Greece till now?
So, well, I had several milestones in my career. One would be when I joined Yale for my PhD. The one I worked for Intel in Silicon Valley, and then joining NYU as a professor. But I would say the biggest epsilon, the biggest change in my life would be when I started my PhD in a new country, because I had never left Greece, and I had never traveled abroad either, and I had never been on a plane either. So the first time I boarded a plane, I left the country and I went to another country, would be when I started my PhD. That would be the most life-defining moment for me, because I went to a place that's far in the United States. I was alone. You feel also exposed and vulnerable. And I went through my depression phases. Most people do. It's normal, actually, to be depressed at some point. You miss your friends, you miss your country, you're alone. You say, why am I doing this, right? No, I'm here struggling. It sucks. But all these experiences, it was extremely useful at the end, because I learned my limits. I learned that I can make it anywhere, right? This feeling that you feel strong enough to do anything, it's actually very relieving. And I'm telling my friends, right? They say, what happens if something goes wrong? I say, I don't care anymore, because I think I'm strong enough to go anywhere. And I don't say that it sounds arrogant, but it is something I don't say out loud, right? Something I think everybody should cross that threshold, that now, no matter what happens, they'll make it. And to be able to cross that threshold, you have to be exposed. You have to challenge yourself and do different things so you understand your limits. And when I was doing my studies in Greece, I was doing all the homework, the projects. I never missed anything. I enjoyed actually computer science. And then I go to the US and I cannot even do half of it, right? Because I don't have enough time. But I did it. I didn't sleep for days. I was sleeping like 1 hour a night and stuff. And I realized my limits are a bit different than I thought. I can actually push myself much harder. Not that you should be doing it all the time, but you realize that you have much more potential that you think you have, because you will only be exposed to a very specific circle of things, right? So when you broaden this up, then you realize you can do much more than you think. So to me, the huge change was going abroad for a PhD. that made a big difference.
Thank you very much, Mr. Manotakos. It was very interesting, was inspiring, hearing the presentation, answering the questions, and telling us a bit about yourself. We're grateful, and thank you once again for accepting to be part of this conference.
I'm grateful for the invitation, Adoni, and it is an honor to speak to young minds. Right, it's not only my job, but I really enjoy it, and I wish I could see you all in person, so we can chat more, and we can just get to meet each other more. But as I said, and I'll say it again, my email is open. Feel free to reach out for advice, for comments, or if you have technical questions, I'll be very happy to talk about them too. Thank you for the invitation.